All right. In section 5.2, we'll be expanding on discrete population probability distributions and be a little bit more specific into what's called binomial probabilities. If you ever watch the show Wheel of Fortune, each contestant has a try at the wheel, right? So the Wheel of Fortune is a roulette wheel with 36 slots, only one of which is gold. If the ball lands in the gold slot, the contestant wins $50,000, or in the TV show, I think it's like $1 million, right? The difference between the TV show and like in the Wheel of Fortune that's being described here is that no other slot pays out. So you either hit the gold slot and win, or you don't. So the question is asked: what is the probability that the game show will have to pay the fortune to 3 contestants out of 100? So in this problem, the contestant and the game show sponsors are concerned about only 2 outcomes from the Wheel of Fortune. Either you land on the gold or you don't land on the gold. Now, the problem that we have here, this type of problem, is typical of an entire class of problems that are characterized by this feature, that there are only 2 exact possible outcomes for each trial. So these are called binomial experiments. Another name for it are called Bernoulli experiments. It's named after the Swiss mathematician Jacob Bernoulli, who studied them in the late 17th century. So here's the features of a binomial experiment. First, there is a fixed number of trials. The trials don't go on and on and on and on. So there's a fixed number of trials. We denote this by the letter N. The trials are independent of each other, and they're repeated under the exact same conditions. And there are only 2 outcomes for each trial, either success or failure. So success is denoted by S, and failure is denoted by F. For each individual trial, so not only does each trial have 2 outcomes, but each trial has the same probability of success and failure. So when we talk about success and failure in a binomial experiment, we denote P, the lowercase p, as the probability of success, and the lowercase q as the probability of failure. And of course, if we know the probability of success, we can calculate the probability of failure by subtracting the probability of success from 1, because they are complements of each other, and there are only 2 outcomes. The central problem of a binomial experiment is to find the probability of a certain number of successes out of a specific number of trials. In the example that we were given, the example says to find the probability that a success is done on 3 out of 100. So in that case, 3 would be R, and 100 would be N. So here's an example. According to the textbook of Medical Physiology, 5th edition by Arthur Guyton, 9% of the population has blood type B. Suppose we choose 18 people at random from this population and test the blood type of each. What is the probability that 3 of these people have blood type of B? So in this experiment, we are observing whether or not a person has type B blood. We're describing a success to be a person that has type B blood. So if a success is a person that has type B blood, then a failure is any other blood type. The probability of success is 0.09, since 9% of the population has type B blood. What is the probability of failure, Q? So if the probability of success is 0.9, that means the probability of Q has to be 0.91, because both of those have to add up to equal 1. Now, in this experiment, how many trials do we have? Well, let's go back. How many people did we choose for these trials? We chose 18 people. So there are 18 trials. We wish to compute the probability of 3 successes out of 18 trials. In this case, R being the number of successes that we want to be 3. Okay? So let's try another example of identifying our correct variables. A certain surgical procedure has an 85% chance of success. A doctor performs the procedure on 8 patients. The random variable represents the number of successful surgeries. So we got to ask ourselves, first off, how many outcomes do we have? Well, either this procedure is a success or it's not a success. So there's only 2 outcomes. For each trial, is there the same 85% chance of success? Yes, there is. It says a certain surgical procedure has an 85% chance of success. Do we have a fixed number of trials? Well, we have 8 patients. That's the number of people that this procedure is being performed on. So yes, it fits that. Let's go back to these, right? So we've already found the fixed number of trials. Are they independent and repeated under the same conditions? Well, I'd like to think that surgeries are done independently and under the same conditions. So yes, we've already found our 2 outcomes. We found our probability of success to be the same. We're trying to find however many successes, right? So yes, so our find the values of N, P, and Q and list possible values of the random variable X. So we're going to let X be the number of successes that we have. Now we did something similar to this where we had 8 total possible outcomes, right? Or not 8 total possible outcomes. We don't have 8 total possible outcomes. We have more than that. So we have 8 trials. Probability of success is 0.85. Probability of failure is 0.15, since 0.85 subtracted from 1 is 0.15. And we also have values of X. So I could have anywhere from 0 successes all the way up to 8 out of 8 successes. So we have 9 possible values for X. And yes, it is a binomial experiment because it passed all of the criteria that we had described it needed to be. Now there are 3 ways to compute probabilities for a binomial experiment. Either we can use a binomial distribution formula, which I'll cover in a second. We can use a binomial distribution table, which can be found in your textbook. And if it's not in your textbook, I will add it to your textbook at some point. And of course, we can use technology. We can use our calculators. We'll go through all 3 of these and just to show you how to find these binomial probabilities. Now, the central problem of a binomial experiment is to find the probability of a certain number of successes after a certain number of trials. Now we'll see how to actually calculate those. Suppose you're taking a timed final exam. You have 3 multiple choice questions left to do. Each question has 4 suggested answers, and only one of these answers is correct. You only have 5 seconds left to do these 3 questions, so you decide to mark answers on the answer sheet without reading the questions. Assuming that your answers are randomly selected, what is the probability that you get either 0, 1, 2, or all 3 questions correct? Now, we're not trying to find the probability of this, or this. We're trying to find the probability of each one of these scenarios. Okay? So, again, this example is considered a binomial experiment because either you get the question right or you get the question wrong. You have a finite number of questions. The probability that you get a question correct is the same for each question. Okay? So each question can be thought of as a trial. So there are 3 trials. There are 2 possible outcomes. Either you find the correct answer or you get the wrong answer. And these trials are independent of each other because we're choosing them completely at random. Now, what is the possibility of success on any one question? So think of a multiple choice question, A, B, C, or D. Only one correct answer. That means that the probability we have is 0.25. 1 correct answer out of 4. Which means the probability of failure is 0.75. And of course, we have 3 trials. Now, what are these possible trials? Well, let's list them out. Since these trials are independent and we are wanting all 3 events to happen, what operation do we use to find the probability? So independent, when we talk about independent versus dependent, we usually talk about the multiplication rule. All right, so for example, what is the probability of a success, and a failure? So since these are all independent, actually, hold on, let's talk about the possible outcomes. So we have 3 questions, either success or failure. It's the same thing with the 3 coins, right? I either have all 3 successes, 2 successes and a failure in any particular order. I have 2 failures and a success in any particular order. or all three failures. So what is the probability of a success, and a failure? This particular outcome. Well, these are independent, so we can use the multiplication rule for independent events. So P of S times P of S times P of F, right? That's 0.25 times 0.25 times 0.75. And I'll round that to 2 decimal places. I'll do 3 decimal places. That's 0.047. That's just the probability of one outcome. Now, as you progress through these binomial probability problems, you'll start to notice that some of the parts in the sample space will have the same probability, because remember, multiplication is commutative. So SSF actually has the same probability as SFS. It also has the same probability as FSS. So all 3 of these have the same probability, 0.047. All 3 of these will have the same probability. And as a matter of fact, the only thing that will change is these 2 will not have the same probability, because you have 3 different P's and 3 different Q's, right? The probability of P is not the same as the probability of Q. If that were the case, then they would have the same probability. However, that's not necessarily the case. Okay. So here's a table that shows all of the potential outcomes. So for all 3 S's, that's P of S times itself 3 times. That's 0.25 cubed, which is 0.016. We've already did SSF, SFS, and FSS. We did that here. Probability of SFF and FSF and FFS have the same. And then the probability of all 3 F's is Q to the 3rd, which is 0.75. But here now we have a value of R, number of successes. So remember, our number of successes was questions that we got right. So for this one, and this one, each of them is a situation where we have 2 correct answers. This one, and this one is a situation where where each of those has 1 correct answer in it. So pay attention to that as we go through the next question. We're going to use these probabilities to find the probability of for our successes out of 3 trials, for 0, for 1, for 2, and for 3. Using the table above, compute P of 1. So 1 is our value of R. Now, in order to get 1 success, I either have to get this, or this, or this. The key word here is or. If I get SFF, that doesn't mean I get FSF at the same time. So that's a good thing for us, because that shows that these events are mutually exclusive. So I just have to add all 3 of these together. So 0.141 plus 0.141 plus 0.141. That gives me a value of 0.423. If I did it in my head, I'm going to put it in my calculator just to make sure. That's 0.423. Yes, that's right. And I would do the same thing for P of 2, right? To get P of 2, to get 2 correct successes, correct answers, I either need to have this, this, or this. And again, since these are mutually exclusive, I just add all of these up. And that gives me what? Probably, I'll just type it in my calculator. 0.47 times 3, that's 0.141. And again, here's a visual breakdown of how that looks, right? So we're transitioning from this table. We found the value for each possible outcome, and now we've condensed them to the number of successes, right? So again, that's where we get all these from. And of course, if I add up all of these probabilities, I do get a value of 1. Okay. What do we do when R is more than 3? So in the previous example, the number of successes that we wanted is equal to 3. But what happens when the value of R is greater than 3? Because we already covered equal to 3, and we've already covered less than 3. But what about R greater than 3? This is where the binomial probability formula is going to come in handy. So here's how it's given to us. It's given in two different forms, and I'll show you why. P of r equals n factorial over r factorial times n minus r factorial times P of r times q, P to the r times q to the n minus r. Now, if this looks familiar to you, it should, because this is actually the combination formula. It's actually the combination formula. NCR times P to the R times Q to the N minus R. So here's our binomial probability distribution formula. And P is the probability of success for each trial. Q is the probability of failure for each trial. R represents the number of successes that we want. And it has to be between 0 and n, right? Because there's only a finite number of trials. And of course, we have the factorial notation, and we have the combinations formula, which you can easily do in your calculator. Now, let's look at using this formula. A card is selected from a standard deck and replaced. So that means we have some independent events here. This event is repeated a total of 5 times. Find the probability of selecting exactly 3 clubs. So let's start with the first part. We're going to identify what each trial is. Well, what is a trial? Well, a trial is a card pull. How many trials do we have? We have 5 total card pulls. What is a success? Success is choosing a club. And failure is choosing anything else. Any other suit. So now we'll identify what our variables are for N, P, Q, and R. So for N, P, Q, and R, okay, we already established that our N was 5. Now, what's our success rate? So in a deck of cards, there are 4 suits, each of them having the same number of cards in them. 13 cards for each suit. So there are 13 clubs in a 52-card deck. That reduces to 1/4. So our success is 0.25, which means our failure is 0.75. And we want to find the probability of selecting exactly 3 clubs. So let's go ahead and use the formula. All right, so P of 3, that's NCR, right? So N5, C3 times my P, 0.25 to the R, 3, times 0.75 to the N minus R. So N minus R, N minus 3 would be 2. So this should be P, this should be Q. The exponents should always add up to your N. So let's go ahead and let's calculate that. So 5C3 in my calculator, here's a refresher. 5 second math, I'm sorry, not second. Start over. 5, press the math button, scroll all the way to right for probability, and choose NCR. 3. Now I'm going to type that number in now and just see what that is. It's 10. So that's going to take 10 times both of these. So 10 times 0.25 to the third times 0.75 squared. And I get a value of 0.088 as a probability of choosing exactly 3 clubs. We can also use a binomial distribution table. In some cases, we'll be interested in just the probability of a range of successes. In such cases, we need to use the addition rule for mutually exclusive events. So the good news is, whether we're using the multiplication rule or the addition rule, we're using the more simplified versions of those rules. So with the multiplication rule, you're just multiplying the individual probabilities together. For the addition rule, you're just adding the individual probabilities together. Okay. So in instance, for a value of 6 for trials with a success and failure rate of 0.5, if I want 4 or fewer successes, That's the probability that my R is either 4, 3, 2, 1, or 0, which means I just add up each of those individual probabilities together. Now, here is a table that's in your textbook called the binomial distribution table. Again, if it's not in your textbook on OneNote, I will add it there shortly. It shows a section for n equals 6. So here's my n value for 6. Here's my success values for R. And each of these is the value of your P, the value of your success rate here at the top. So for P equals 0.5, here are the different probabilities that you have. So I want to know 4 or fewer successes. So if I want to know 4 or fewer successes, then I take all 4 of these probabilities, or all 5 of these probabilities here, and I just add them up. Because that's the addition rule, right? 0.16 plus 0.94 plus 0.234 plus 0.312 plus 0.234, and I get a total of, wait, hold on a second, 0.016 plus 0.094 plus 0.234 plus 0.312 plus 0.234. And I get a probability of 0.89, so about an 89% chance. Now, what if R was greater than 4? Now, I'm going to cover that a little bit later, but in short, if R is greater than 4, it means it's definitely not one of these values. Well, the good news is I can actually take this probability and subtract it from 1, because that's the complement. That's the so 4 being greater than 4 is the opposite of 4 being less than or equal to 1. So these two are complements of each other. So if I take the probability that I already have and subtract it from 0.89, I get 0.11. Now, when we calculated this, we got 0.89. What's another way to find that probability? Well, again, it's to use the complement. 1 minus the probability of R equal 5 or R equal 6. Right? That's R greater than 4. And if I add those up, I do get 0.11, which is 0.89. So we can still use complements to try to figure this stuff out here. Okay. All right, let's try this example here. About 10% of workers age 16 and older in the US commute to their jobs by carpooling. You randomly select 8 workers. What is the probability that exactly 4 of them carpool to work? So what is a trial? Well, a trial is selecting a worker, which means that a success is given by the carpool. That person carpools. And a failure is no carpool. So now let's go ahead and identify no carpool. Let's go ahead and identify N, P, and R. What's our N? What's our trials? How many people did we randomly select? 8. It says about 10% of workers in the US commute to their jobs by carpooling. So if we choose a success, that means it's a person that carpools, which is 1 out of the 10% of the population, which means my Q is 0.9. So I can use the probability formula on this to find the probability that exactly 4 people carpool to work, or I can use the binomial distribution table to figure this out. Let's see. Here we go. Hold it at the right spot too. All right, so here's an example of a binomial distribution table here. So I'm looking for value of n being 8, which is this first white column here. So R is 4. That's this value right here. So now what I'm going to do is I'm going to find my value of P to be 0.1, which is the same as 0.10. So I'm going to match that. Use this here. 0.1. So I'm going to match that to my R being 4, which is here. So that's about right here. Probability of 0.005. That's using the binomial distribution table. So my probability ended up being 0.005. If you wanted to, you could use the formula, right? So 8C4, if I calculate that first, I get 70. So 70 times 0.1 to the n to the eighth, no, to the r, no, sorry, 4 to the fourth, times 0.9 to the 8 minus 4, which is also 4. And if I round to 3 decimal places, I still get the same answer, 0.005. About 55% of small businesses in the US have a website. You randomly select 10 small businesses. What is the probability that exactly 4 of them have a website? So you work this the exact same way. How many small businesses do we select? That's 10. So N is 10. Probability of success is 55%. So P is 0.55. And then Q is 0.45. And I'm looking for an R of exactly 4. So if I go back to my table, and I look for N being 10, which is right here, and my R being 4, that's right here, I'm going to find my value of P being 0.55. So P being 0.55, that's this column here. I'm going to go all the way down here to, let's see, that's about, sorry, my hand's getting in the way. 5 down here. This is 0, 1, 2, 3, 4. That's a probability of 0.16. So as long as you have the table, you could also you could also refrain from using the formula, right? So that's using the table. So we've already worked using the formula. We've already worked using the table. Your graphing calculator actually does have a binomial probability calculator on it, a binomial probability function. For this operation, you need N, P, and R. Okay, you need your N, your P, your R. When you type this in, some of the older TI models require you to actually type in all these numbers in with commas, but some of them, like this one, if I press second variables and I scroll down to get binom PDF here, it actually gives me a menu to choose from. And when I complete this menu, it'll paste all these values into that calculator function. Okay. But there's also binom CDF. Now, what's the difference between the two? It has to do with this versus this. Binom PDF is for when you want to calculate the number of exact successes. R equals some number. But binom CDF is for R or fewer. R less than or equal to some number. So PDF is for an exact value. CDF is for that value and lower. Now here's the thing. Your calculator does not have a binomial probability distribution function for greater than or equal to. But that does not mean that you can't calculate it using a calculator. Just like we did earlier, right? Let's say my R was greater than or equal to 4. Then I could just take 1 less than 4, like this, 3. Now, if this were just simply greater than 4, well, then that changes, because now my R actually can be 4 when I do the complement. And we also get something similar if we have R. Now, if we, let's say we have, erase this real quick here. Let's say we just have R strictly less than 4. Well, I can't use a binomial CDF because CDF is 4 less than or equal to. But if I go one number down, that's the same thing. And I could use a binomial CDF with that value. But enough talking about it, let's actually practice this. The results of a recent survey indicate that 67% of US adults consider air conditioning a necessity. You randomly select 100 adults. In this example, what's N, what's P, and what's R? Well, I don't know what R is. I want the probability that exactly 75 adults consider air conditioning a necessity. There's my R. So my N, that's how many people that I'm selecting in total, 100. What's my probability of success? 67%. So P equals 0.67. My R is 75. So I'm going to put this in my calculator as this. Binomial PDF. And again, because this is an exact value, an exact number, I'm going to use a PDF calculation. NPR. So 100, comma 0.67, comma 75. So in my calculator, this is how I'm going to type it out. So I'm going to press second variables. I'm going to scroll down until I get to binomial PDF, enter. Now this calculator has the menu for it. So I'm just going to type in the values for each part of the menu. How many trials do I have? 100. What's my value of success? 0.67. What's my X value? 75. So when I press enter twice, here it is. There's the formula all typed out in my calculator for me. I'm going to press enter, and here's my value, 0.020. Or 0.02, 2% chance. Now, what is the probability that 75 adults or less consider air conditioning a necessity? So this is 75 or less. Instead of R equals 75, this is R is less than or equal to 75. This time it's a binomial CDF calculation. So binomial CDF, 100, comma, 0.67, comma, 75. So I'm going to do the exact same thing in my calculator as last time, except instead of binomial CDF, I'm going to go one down and choose, instead of binomial PDF, I'm going to go one down and choose binomial CDF. And again, 100 trials, value of P of 0.67, and an X value of 75. And there it is. It's all pasted in for me. Press enter, and I get a value of 0.967. 0.967. So here's another example. A survey found that 34% of US adults have hidden purchases from their spouses. You randomly select 200 adults with spouses. And what is the probability that exactly 68 of them have hidden purchases? What is the probability that 68 or less have hidden purchases? It's the exact same type of problem. N is 200, P is 0.34, and R is 68. And so again, exactly 68, that's binomial PDF. 68 or less, that's binomial. I'm going to do the exact same type of formula that I used here. So binomial PDF 200, 0.34 and 68. And I get 0.059. Then I do binom CDF for 75 or for 68 or less. So 200, 34, 68. And I get a value of 0.533. Now, what does the binomial probability distribution tell us? Well, again, you have the same, when a binomial probability distribution is used, we know the sample space of events because we need the number of successes we need for each possible event. The binomial probability distribution gives the values of P of R. It gives the probability of R successes out of the N trials for each R between and including 0 and N. And then the calculation of P of R depends on the probability of success, the value of R, and the value of N. And that's whether you're using the formula, whether you're using the table, or whether you're using your calculator.